In power electronics, we often need to convert alternating current into a form that can be used for DC applications. While pure AC averages to zero over a full cycle, rectification changes the game by flipping the negative half-cycle upward. A full-wave rectifier ensures that current flows in the same direction during both halves of the AC cycle. This creates a pulsating DC waveform where the polarity is constant, but the magnitude still varies with time. To find the average precisely, we look at a single pulse from 0 to pi. We define the instantaneous current as the peak value times the sine of the angle. This mathematical model allows us to calculate the area using integration. We set up our integral by taking the height of the function across the interval of one pulse, which spans from 0 to pi radians. Dividing the total area by this interval length gives us the mathematical mean. By performing the integration, we find that the integral of sine is negative cosine. We then evaluate this from 0 to pi. This step-by-step calculus reveals how the curvature of the wave contributes to its average value. Evaluating the limits gives us a value of 2. When we multiply this by our leading constant, we arrive at the final relationship between the peak value and the average value of the full-wave rectified signal. The mean value of a full-wave rectified current is exactly 2 times the peak current divided by pi. This roughly equals 63.7% of the peak value, a constant ratio for any sinusoidal input. Let's apply this. If you have a rectified wave with a peak current of 10 amperes, the average DC current delivered to the load would be 6.37 amperes. This is the value a DC ammeter would display. For a standard 230-volt RMS supply, the peak voltage is about 325 volts. After full-wave rectification, the mean voltage becomes approximately 207 volts, assuming no diode losses. It is important to note that the full-wave average is exactly double that of a half-wave rectifier. Because we are utilizing both halves of the cycle instead of blocking one, the efficiency and average output significantly increase. Even if the frequency of the AC source changes, the ratio between the peak and the mean remains the same. Whether it is 50 Hz or 60 Hz, the average value is always determined solely by the peak amplitude. Conceptually, the mean value creates a rectangle with the same area as the area under the sine curve. This area equivalence is why the average value is so useful for calculating total charge transfer in circuits. In practical terms, this mean value is what determines the charging rate of a battery or the speed of a simple DC motor connected to the rectifier. It represents the useful DC component of the pulsating signal. To summarize, full-wave rectification provides a continuous stream of positive pulses. The mean value is calculated via integration over pi radians, resulting in a value that is roughly 64% of the peak amplitude. Let's test your understanding. If the peak voltage of your AC signal is exactly 100 volts, what would be the mean value after passing through a full-wave rectifier? Think about the constant we derived. The correct answer is 63.7 volts. By multiplying the peak by 0.637, we find the average. Thank you for joining this lesson on electrical fundamentals. Generated by Vision Solve AI.